We're going to find the volume of the solid of revolution obtained by rotating the region bounded by the graphs of the parabola y equals 2x squared, the line y equals x, and this region is going to be rotated about the x-axis to generate the solid of revolution. So first let's go ahead and sketch this region. These are two familiar functions, so it shouldn't be too difficult to do. This is what the parabola looks like in the second quadrant. We really need its graph in the first quadrant, and then the line comes through like that. You can see that there are 2 points of intersection, one over here, one over here. We can find them by just inspection, but the formal way of finding them is to set the right hand sides equal, x squared equals x, then move everything over to the left. X squared minus x is 0. So factor in x times x minus 1 equals 0, and x equals 0 or 1. So we have two values of x. The interval is between 0 and 1, and the region that will be rotated is right over here. So now let's go ahead and see what the solid of revolution looks like. We're not going to draw the entire solid. The entire solid can be drawn on a computer algebra system such as Maple or Mathematica, but all we need is just to draw the original region, which is right here. The axis of rotation is the x-axis, and then when the rotation is 180 degrees finished, it ends up in the fourth quadrant, the region does, and this is what it looks like. We just reflected about the x-axis. This is 1, so our interval is between 0 and 1. Now select any x between 0 and 1. So here's a typical x. Keep track of this vertical piece of the area of the original region. Then 180 degrees into the rotation. This area will end up over here in the fourth quadrant. And as you can see, if we now take a cross section of our solid, which is the entire 360 degree rotation, our cross section looks like this washer with a little bit of thickness to it. So this is the cross section of our volume. All we have to do is find the area of this washer as a function of x, then multiply it by, just as I said, a little tiny interval, the length of a tiny interval, which gives it thickness, gives it volume, and then integrate from 0 to 1, because that's where all our washers are. So we need to review a couple of things. This is the original region again. What is an area of a washer? So I'll draw a washer right over here. It has an inner circle and then the big circle. Let's say that the radius of the inner circle is little r, and then the area of the big circle is big R. And we want to find the area between these two circles. It's pi times big R squared, that's the area of the whole big circle, minus pi little r squared, that's the area of the small circle. That gives us exactly the area between the circles. So we can simplify it. Pi big R squared minus little r squared. So in our case, for any x, here's my x, big R would be this right there. That's our big radius. And the little radius is going to be this part right over here. So the big radius is the whole thing, little radius is that part. And we're going to now integrate from 0 to 1. That's where all our slices are. So the volume of the solid will be the integral from 0 to 1 pi times the big radius. Now the big radius is the y coordinate on the line. That's x, so we square that. That's the big radius, minus the little radius is on the parabola, that's x squared, and we square that. And this difference times pi integrated, we give it a little bit of thickness, dx, that gives us the volume of one of those slices, the washer slices. The integral serves as the sum between 0 and 1, and once we integrate it, we're going to get the entire volume of the solid of revolution. So this is the integral from 0 to 1, x squared minus x to the fourth, which is equal to pi times The integral of x squared is 1/3 x cubed. The integral of x to the 4th is 1/5 x to the 5th, evaluated between 0 and 1. So this is just pi times 1/3 minus 1/5. And the common denominator is 15, so we have 5 over 15 minus 3 over 15. We end up with 2 pi divided by 15